Okay, so this is a video taking you through question 1 of the Unit 8 end of topic test. So, let me see, is at the bottom, sorry. Alright, so we are preparing cyclohexene from cyclohexanol. So this is a dehydration reaction. We're losing water, so it's an elimination, but this isn't really about the mechanism. And it says a student prepared cyclohexene by placing 10 cc's of cyclohexanol with this density. So I know that I'm going to be able to calculate the mass of that, because I can say density equals, so it's mass divided by volume. Oh, sorry, so therefore we're going to have M equals D times V. Okay, 3 cc's of concentrated phosphoric acid, that's a catalyst, were then added to the flask with some anti-bumping granules. Okay. Now, obviously you've all read this, so I'm not going to spend too much time on that. I'm just going to skip to the question. So it says the student collected 5.97 grams of cyclohexene. So I'm just going to label that with actual yield. So that's how much, sorry, you can't see that, can you? That's how much they actually got when they did the experiment. Therefore, we need to calculate, first of all, the first thing we need is the theoretical yield. Okay, so let's calculate then the mass of cyclohexanol, and that's then going to enable us to calculate the expected mass of cyclohexene. So where are we? We're going to have, we've not got much space here, so apologies about the printing. So we're going to say density 0.96 multiplied by the volume is going to give us, is that right? Yeah, it's going to give us a mass of 9.6 grams. So that is mass of cyclohexanol. Therefore, the moles of cyclohexanol, so moles equals, where are we? Mass divided by MR. So 9.6 divided by the MR of cyclohexanol, and that is 100. So 9.6 divided by 100 gives us 0.096. So that's the moles of this that we have, 0.096. There is a ratio that exists here of 1 to 1, which means we also have 0.96 moles of cyclohexene. Now we need to calculate the mass. So mass equals MR times moles. The MR of cyclohexene, if you calculate that, equals 82. So 0.096 times 82 gives you your mass, your expected mass, your theoretical mass, which is 7.87. Okay, I'm just going to come back down here. So our actual yield was 5.97. Our theoretical yield is 7.87. So we're going to say 5.97 divided by 7.87 and then times that by 100, and that is going to give you a percentage yield of 76%. Okay, right. So next question, test tube reaction on the product, which had a carbon-carbon double bond, it's an alkene, to show that cyclohexanol has been dehydrated. So to test for the presence of a carbon-carbon double bond, you use bromine water, and you would expect it to have a colour change of orange to colourless. Why do we use sodium carbonate solution? When you read through the method, it says that that is added, and you have done this yourself in CPAC. I can't remember, it's been so long now. 5, I want to say, yeah, 5, I think. Suggest why we add the sodium carbonate solution. Well, if you remember, we have a phosphoric acid catalyst. So if you add a metal carbonate to an acid, you will get a neutralization reaction. So it neutralizes the H3PO4. Now, as it does that, that causes, you add a carbonate to an acid, you're going to produce CO2, which obviously is a gas. So that's what the next question is about. Explain why it is important to open the tap of the separating funnel periodically. If you remember, you do that kind of, you sort of turn it up and down, you invert it repeatedly, and then periodically you remove the stopper. Hopefully your teachers explain to you why you're doing that, and that's because of that. So it basically, I'm going to say, prevents build-up of gas pressure, or pressure of gas. That's very poorly written. Now, you don't have to specify actually that it's CO2, but if you do specify a gas, you must get it right. Okay, a property of anhydrous calcium chloride other than its ability to absorb water that makes it a suitable drying agent. Now, I think if you took the mark scheme, you can't just say it's unreactive. You need to specify that it doesn't react with the cyclohexene. That's your product, okay? So that's the thing you don't want it reacting with. You just want it to dry out any water that might be left in that product even after you've done the separation. Okay, describe the apparatus used to remove the drying agent by filtration under reduced pressure. Now, this is a bit of a nasty question because actually I don't think you've done this technique in CPAC 5. It comes up when you make your aspirin. So you use something called a Buchner funnel, which looks like this, okay? So this is your conical flask. In here, this bit here, this white bit, this is the Buchner funnel. And inside there, so let me just, if I get rid of that a minute, that has, this one shows it quite nicely, this like a cross section through it. This has perforations in it, and you put some filter paper on it with the thing on top that you want to dry, and then you, the conical flask, you can see here, the conical flask that it's attached to, in fact this is a nice one here, the conical flask here has a side arm that you attach some rubber tubing to, and then you attach that to a vacuum. In fact, you just attach it to a tap actually, and you create a vacuum, and so it sucks basically any remaining water gets sucked, or any, in fact any not water, sorry, any sorry, I'm talking rubbish. Your product in here will have your drying agent in it, okay, your calcium chloride. As when you switch on the vacuum, it sucks all of your product, the desired product, into the flask, leaving on this slightly damp piece of filter paper the drying agent that you don't want, and then you discard that and you're left with just your pure product, okay? So when you're asked to draw it, in fact you don't have to draw it, but if you can, then it is the easiest way to pick up the marks, because then you just need to label it. This diagram, to be honest, gives way more labels than you need, but I think sums it up very nicely, because what you'll notice here is that there's no blockages. Very common mistakes is the bung. People will draw across there and there and block it. The side arm here, people will block that, okay? Any blockages where there should not be blockages, you're not going to get the mark. Equally, if things are sealed where they shouldn't be sealed, then you're not going to get the mark, okay? So, I'm not going to draw it. That's what it looks like. You can Google it at your leisure if you want. Okay, so G takes us on to more separation. Sample of cyclohexene has been contaminated with cyclohexanol. The cyclohexene can be separated from the hexanol by column chromatography. So silica gel is a stationary phase. Silica gel is polar. If you're not sure what the structure of silica is, look it up. And that's our stationary phase. And hexane, which is non-polar, is the mobile phase. Cyclohexene is non-polar, and cyclohexanol is polar because it's got the OH group. So does silica. Okay, therefore we would expect our cyclohexene to have greater affinity for the mobile phase, and we would expect our cyclohexanol to have a greater affinity for the stationary phase. So let's have a look and see what the question then says. Explain why a shorter cyclohexene has a shorter retention time than cyclohexanol, and this is 2 marks. So the first thing you're going to want to do, and I'm not actually going to answer it, I'm just going to right here, you're going to state the polarities, and the second mark is you're going to relate that to mobile / stationary phase affinity. Okay. Right, last part of this question. Explain how an infrared spectrum would confirm that the cyclohexene obtained from the chromatography column did not contain any cyclohexanol. This is only 1 mark, and there are a couple of things you could say here. You could talk about what the peaks that you would get if you had a carbon-carbon double bond, or you could talk about the absence of an OH bond. Now, annoyingly, I've lost my periodic table or my data sheet, so I don't have the values, but you should have it in front of you. And if I were answering this, I would say there would be no peak at 300, what is it, 3230 2350, I'm running out of space here, centimetres cubed, due to OH. Now, a bit of a tip for answering questions on IR spec. Quite often, if you do not put the group like that for an OH, if you don't put O bond H, you don't get the mark, because it's this bond that is causing that peak. So they quite often want to see the bond between the O and the H. So whilst you might know that, you think that's an easy mark, you might lose it on technique. So something to be wary of. I don't think they're that fussed particularly in this question. Oh, where's the marks for you? No, I think it's okay. But anyway, okay, that's question 1.